Just give me 2 minutes. I'm trying to share my screen.
Okay.
Are you able to see my screen now?
Yes, sir.
Yes, sir.
Oh. Okay, so good evening, everyone. Welcome to this course on failure analysis and design. So my name is Ratna Kumar. I'm a faculty member in the Department of Mechanical Engineering at IIT Madras. I work in the area of computational mechanics and granular soft matter, to be precise. So I've been teaching this course. I've taught at least 3 batches of web-enabled MTech students this particular class, and I've also taught similar courses for MTech and PhD students on campus. So with that background, we will start the course. But before we start the course, I would like to understand the composition of this class, right? So it would be really nice if you can switch on your videos, all of you, and introduce yourself one after the other. Maybe to avoid the confusion, I will call on the names so that you can introduce yourself. I see that there is one team, Mr. Arunachalam M. A group of participants are sitting together, and one of you must be Arunachalam. Maybe we will start with this group, and if you don't mind, one of whoever is introducing yourself can come to the camera, close to the camera, so that I can see, and also other participants get to see you, at least today. And then tomorrow onwards, I may not ask you to come close to the camera, but I would like to hear your voice in terms of questions. Okay, so can we start with, so you please give your name and your organization, where you did your bachelor's and when did you do? Which year have you done your undergrad? And how long have you been away from academics? So in the classroom setting. So this is something that I would like to know to get an idea of what the composition of this class is. Is that okay?
Yes, sir, it's okay.
Yeah.
So I'll start from myself, Arunachalam.
Mr. Arunachalam, I'm not able to see you. So, okay, maybe I will pin you.
1 minute.
So pin that
Yeah.
video, whoever is speaking. Yeah, now I can see. Yes, please.
Yes, myself, Arunachalam. I'm working in Mahindra and Mahindra, MRV, Chennai, sir.
Okay.
In Mahindra University. I did my bachelor degree in Karaja College of Engineering, Madurai, year 2011.
2011. Okay. 14 years ago. Yeah.
Yes, sir. 14 years.
Okay. So is this so coming back to the classroom after long?
Yes, sir. I am the
14
only
years.
person coming up here.
Okay, great. Yeah. So next.
Hi.
Yeah, please go ahead. Yeah.
Myself, G. Anand Kumar, working with Mahindra for past 15 years.
Anand Kumar, what is the name?
G. Anand Kumar.
Anand Kumar. Okay. Yeah.
So I am working with Mahindra for past 15 years. Engine development center for 12 years, and right now with the brake system for 3 years. I have completed my graduation from IRTT earlier, Institute of Road and Transport Technology, 2005.
2005. Okay. All right.
Yes. Thanks.
Hi, sir. Myself, Vijay Raj. I'm currently working in Mahindra and Mahindra. I did my bachelor's in mechanical engineering in 2012. Yeah, yes, sir. Nice to meet you, sir. Good evening.
So where did you do your bachelor's from?
In Tamil Nadu College of Engineering.
Okay. Tamil Nadu College of Engineering.
Yeah, yes.
Okay. 1 minute. I think there seems to be some urgent call coming, please.
Yes.
Okay, please. Yeah.
Am I visible, sir? This is
Yes,
Prem
yes,
Vinayak.
I can see you. Oh, you are in two cameras. Yeah, Prem Vinayak. Yes, yeah.
I'm not unmuting on my laptop, but my video is visible.
Okay, perfect.
So, my name is Prem Vinayak, and 1 second. Yeah, I've joined Mahindra 5 years back. So, not technically 4.5 years. So, as a GET, 2020, I passed out from college. I did my BTech in Sairam Engineering College in Chennai. 2020.
Okay, yeah. All right, next. Yes, yeah.
Yes, sir. My name is Aditya Kumar. I am in FD Hydraulics with Mahindra and Mahindra for almost 7 years. But I am in notice period, so in next 1 month I will be joining my next organization. And I have a total of 12 years of experience mixed in pneumatics and hydraulics. I did my BE from Don Bosco Institute of Technology in 2013.
Okay. All right, yeah. Next.
Sir, Titus here. Can you see me, sir?
Yes, I am able to see all of you. No worries. Yeah.
Yes, sir. So I'm Titus. Actually, I did my undergraduation from Tyagarajar College of Engineering, Madurai in the year 2017. And I joined Mahindra immediately after that as GET. So I'm having total of 8 years of experience in Mahindra. In that, 4 years into CAE structural durability and remaining 4 years into CAE vehicle dynamics.
So 2017 you graduated.
Yes, sir. Yes.
Okay.
Thank you, sir.
Yeah. Next.
Sir, I'm Lakshmi Narayanan. I am working in Mahindra for past 6 years. My domain was engine calibration and in Mahindra Farm Division. I have completed my engineering in 2014.
Okay.
at Tirumala Engineering College under Anna University of Technology in Chrome. I have completed.
Okay. Yeah. Last one in the team.
Hello, sir. My name is Vallesh. I finished my mechanical engineering from AMC Engineering College, Bangalore, in the year 2014. I've been with Mahindra since 2017 in the vehicle architect department.
2014, you have finished your BTech?
Yes, yes, yes.
Okay. And you're the previous person also in 2014?
Yes, sir, yes.
Yeah. Okay. All right. So next we'll go to Vikas.
Good evening, sir. Myself Vikas Paul, and I did my BTech from VNIT Nagpur, and I have joined Bajaj Auto in 2013 when I did my BTech. So I'm in research and development department and working in powertrain development.
Bajaj Auto. When did you join Bajaj Auto?
2013, sir.
BTech in
VNIT Nagpur, mechanical engineering.
2013?
13, sir. Yes, sir.
Okay. Are there anyone else from Bajaj, or you are the only one?
Yes, sir. There is one more person, Mr. Roshan Kumar.
Okay. So maybe Roshan did not switch on his video yet. So let me see who am I seeing. Mr. Jagan MS. Jagan, you are unmute. You have to unmute yourself. Yeah. Okay. While Jagan fixes his microphone, we will go with Vigneshwaran.
Good evening, sir. This is Vigneshwaran. I'm from Mahindra and Mahindra Limited. I joined Mahindra in 2017. I graduated from Sri Venkateshwara College of Engineering, 2012. Well, I am into engine development testing for almost past 13, 14 years.
Okay. Great. Thank you. Vivekanand.
Good evening, sir. I am Vivekanand. I am in Mahindra engine calibration team for past 12 years. I completed my BTech from mechanical engineering and BE from mechanical engineering from Sri Muthukumar Institute of Technology in 2008.
2008.
Yes, sir.
Okay, great. Yeah, Mr. Jagan, were you able to fix your microphone? Yeah.
Yes, sir. Sorry, sir. I had some issue with my
No
device.
problem. Yeah.
Sir, yes, sir. Myself, Jagan here. I passed out. I'm basically graduated from marine engineering, and I graduated in 2006 from Sri Venkateshwara College of Engineering in Sri Perumbudur. And I sailed as an engineer on board ships. And then I was working with Hyundai Heavy Industries in Singapore for 5 years. And then now I'm working with a company called as V Ships, where we are managing ships. So I'm handling vessel performance services teams as a lead. So total, I have around 19 years of experience, sir.
Okay, great. Yeah, thank you, Jagan.
Thank you,
Rahul,
sir.
Rahul B.
Yeah. Hi, sir. Good evening. So myself, Rahul. So I'm working in ZF commercial vehicle control systems. So basically, braking systems for commercial vehicles and pneumatic braking and so on. And for the past 5 years, so I joined here as a GET in the year 2020. I completed my bachelor's in engineering from specialized in mechanical engineering from SSN College, Chennai, in the year 2020.
2020.
Yeah.
Okay. So far, you and one person from Mahindra are the youngest in the team.
Yeah,
okay.
Prem.
Okay. All right. So next we have ME24M524. I don't know the name. The name is not there. Yeah.
Hi, sir. Good evening.
Yeah.
I am Kirti Shailaja. I am working in lab research as a component engineer. I completed my BE in mechanical from Keli Technological University, Hubli, and in the year 2021.
Okay. So you are the youngest.
Yes. Okay. Currently.
Yadav, Ramanand.
Yeah, hello sir, good evening. I am Ramanand Yadav. I have completed my graduation in year 2015 as a mechanical engineer. I am from Pune, completed my engineering from College of Engineering Ahmednagar, affiliated by the Pune University. Currently, I am working in Tata Elxsi Limited in the Pune.
Tata Elxsi.
Yeah.
2015 you graduated. Okay. I have 231039994.
Sir, good evening, sir. I'm Prabhakaran. I completed my BE Mechanical Engineering in Coimbatore Institute of Technology in 2012 and joined as a GD in Mahindra. And I'm now working in engine calibration, alternative fuels technology. Mostly it's a commercial vehicle, CNG calibration, CNG engine calibration. So from almost 13 years experience in Mahindra, sir.
Yeah. So please consider adding your names when you are joining through Zoom. Okay. So that I can identify. I can ask questions by calling names rather than numbers. Okay.
Yes, yes, sir. Yes. Thanks.
Thank you. Naveen. 24M527 Naveen. Yeah.
Yes, sir, good evening. I am Naveen. I completed BTech in Mechanical Engineering in 2015 from Annabattula College of Engineering and Technology in Tirunelveli. And currently I'm working at Upgrade Materials. So I joined here 1 month back. Yeah. Earlier, I'm having almost 8 years of experience.
Okay. Thank you, Naveen. Jagdish 523.
Good evening, Professor. I'm myself Jagdish. I work at Lamb Research. I have around 7 years of experience in design and development team. I have done my bachelor's in 2017. So I've passed out from the college called KLS VDRIT Haryal. It's in North Karnataka side. Yes.
Okay.
Thank you.
Yeah. 1 minute. Yeah. So next, Yusuf.
Hello, sir. Am I audible?
Yes, you are.
So my name is Yusuf. I work for a company called Twesta Manufacturing Solutions. So we are into concrete 3D printing. And I did my BTech in IIIT DM Kanchipuram. And I passed out in 2021.
Okay. All right. Thank you. Hemant.
Good evening, sir. Can you hear me?
Hemant, you need to unmute yourself.
Yeah. Good evening, sir. Can you hear me?
Yes.
Yes, sir. Myself, Hemant. I am currently working in Mahindra Vehicle Architecture Department from 2019. So
Okay.
I have completed my BTech in Mechanical Engineering from Sri Vidyaniketan College, Tirupati, 2019.
2019. Okay.
Yes, sir.
Okay. Thank you, Hemant.
Thank you, sir.
And Ashwath.
Good evening, Professor. My name is Ashwath Pujari. I work at Lamb Research as a senior manufacturing engineer. I have overall 6 years of experience. I completed my bachelor's from mechanical engineering in the year 2019 from NMAM Institute of Technology, Nitte, Bangalore.
Okay. Thank you.
Thank you.
Who else? If you switch on your videos, then I can identify who I need to call. Yeah. Okay. So, Wavar Meeran or
Yes, Professor.
Wavar Meeran?
Yeah,
Yeah.
Vavar Meeran. Yeah. My name is Vavar Meeran. I work at Boeing. I have completed my undergraduation in mechanical engineering 10 years ago from PTR Engineering College, Madurai.
When did you graduate? 2015?
2015, yes.
Okay, great. Yeah. I think Ashwath, we are done with you, right?
Yes, sir.
Yeah. Okay. Pranab. Pranab, you need to unmute.
Hello, everyone. I hope I am audible.
Yes.
Good evening, sir. Myself, Pranab Pradhan. I completed my BTech in 2007 in mechanical engineering from University College of Engineering. It's one of the oldest college in Orissa. And after that, I started working for Applied Materials for 4 years. And then I'm with GE Renewables since then till date. So in GE Renewables, I have 14 years of experience, and in Applied Materials for 4 years. I I graduated in 2007 for BTech.
Okay, thank you, Pranav.
Thank you, sir.
Vivek Raja.
Good evening, sir. Can you hear me?
Yes.
Yeah. So I am Vivek Raja. I have completed my BTech in Madras Institute of Technology in the year 2012. Currently, I am working with Nordex India.
Nordex India. Okay.
Yeah.
What do you do there?
I am working in the loads validation.
For?
Loads validation for the wind turbine.
Wind turbines. Okay.
Yes, sir.
Hassan.
Good evening, sir. This is Hassan. Working with Mahindra and Mahindra in Delhi to working department. I taught my BTech in 2010 in mechanical engineering from Uttar Pradesh Technical University, Northern India Engineering School.
Okay, thank you. Haider Ali. Maybe we will go with Sharath.
Hi, sir. Good evening. Hello, everyone. My name is Tarath, and I completed my bachelor's in mechanical engineering in 2016 from Sri Krishna Institute of Technology. And after that, I joined Waptec Corporation as a graduate engineer trainee, and it's been almost 9 years now. And I work currently, I'm a lead engineer, mechanical design.
Okay. Yeah. Srikanth or?
Hi, hello everyone. This is Srikanth. So I'm currently working with Caterpillar. I completed my BE Mechanical Engineering from St. Peter's Engineering College, Chennai, in 2011, and I've been working with Caterpillar for almost 6 years now.
Okay.
Thank you.
Thank you. Arun Kumar.
Hello, good evening, Professor. My name is Arun Kumar. I have completed a bachelor's in aeronautical engineering in 2011 from Kumar College of Technology, Coimbatore. Currently, I'm working in Boeing India Private Limited, Chennai. For the past 12.5 years, I'm working as a structural analysis engineer. I do stress analysis of various aircraft components like wings, fuselage, and various interior components. Currently, I'm working in Chennai office at DLF Boeing.
Okay. Thank you.
That's
Akash.
Thank you.
Yeah, good evening, sir. Myself, Akash. I have around 3 years of experience, and currently I work for Boeing, and I work as a structural design and analysis engineer. I've completed my graduation in the year 2022 as an automobile engineer, sir.
Okay. Thank you, Akash. ME24M529.
Yeah, hello, sir. Myself, Prabhakar. I'm from LAM Research, Bangalore. I have altogether 14 years of experience. Mainly, I work on structures and fluid mechanics. So, I'm from University Vishweshwara College of Engineering from Bangalore, 2009 pass out.
2009. Okay. 24M533.
Hello, sir.
Yeah, hi.
You can call me Satish. I'm working at Nordex in Chennai, and I graduated my bachelor's in mechanical engineering during 2020, and I have around 4.5 years of experience.
Okay, great. Thank you. And who else? Others who have not introduced yourself, can you please switch on your videos? Yeah, now I have. Purushottaman.
Yeah. Hello, sir. Good evening. So myself, Purushothaman. So basically, I'm an aeronautical engineer. Completed my undergraduation from Mohammed Sadak Engineering College, Ramanathapuram, in the year 2013. And I am currently working with Boeing India Private Limited as a recruitment lead focal.
Okay. Yeah. Thank you. Roshan Kumar.
Namaste, Professor, sir. I am Roshan. Basically, Roshan Kumar, basically from Bajaj Auto Limited. I have completed my mechanical engineering degree from NIT Durgapur in 2005. And since then, I am working in R&D division of Bajaj Auto Limited. Thank you so much.
Okay, thank you. And Rakshit.
Good evening, sir. This is Rakshat. I'm currently working as a senior mechanical engineer at Lam Research, Bangalore. I have passed in mechanical engineering. I've done my BE from RV College of Engineering in mechanical engineering from in 2022. So yeah, it's
Okay.
been. I have an experience of 4 years, 3 years.
Okay. Thank you.
Thanks.
ME24M525.
Yeah. Hello, sir. Good evening. This is Likita VC. I've completed my UG in Ramaya Institute of Technology. I've passed out in the year 2022. So I have overall experience of 3 years. I'm currently working at Caterpillar as a manufacturing engineer.
Okay. Who else? Hariharan. Hariharan, have you introduced yourself? ME24M522. No. Sushant?
Hello, am I audible?
Yes.
Yes. Good evening, everyone. Good evening, sir. My name is Sushant Rao. I graduated in the year 2020 from Parul University, that is in Vadodara, Gujarat. And we are into manufacturing of electrical furnaces and ovens for various heat treatment purposes.
Okay.
Thank you.
All right.
Yes.
Who else?
Yes, sir. Can I give my intro?
Yeah, Hariharan, yes, I can hear you now.
Yeah, sorry for the glitches. I'm just coming back to my home from office. Yeah, myself, Hariharan Gurumurthy, and I am associated with Caterpillar India Private Limited for 8+ years, and I graduated at 2016 at Sri Sairam Institute of Technology.
Thank you.
Chennai.
Siddharth?
Yes, sir. Good evening. My name is Siddharth. I completed my bachelor's from Mangalore Institute of Technology in the year 2022 in mechanical engineering. I joined Collins Aerospace as a GET from them. Lately, with a business acquisition, now I am working in Safran, Electronics and Defense.
Saffron, okay.
Yeah. Thank you.
Great, thank you.
Am I audible, sir?
Yes.
Yeah. Myself, Heather, and I work in Lam Research, and I have experience of 10 years. I graduated from Lovely Professional University, LP, Punjab, in 2015.
2002.
15.
16.
15, sir. 2015. 2015.
15. Okay. All right. Yeah. All right. Is there anyone else that I could not?
Hi, sir.
Yes.
Sir, Keshav.
Yeah.
Keshav, I cannot see you.
Yeah, hi, sir.
Hi.
Hi. Sir, I'm Keshav. I'm working in Mahindra at AC Tech Karaikudi by 2011. And then I started working in Brakes India as a brake system designer. Now I'm leading a team over here and then into design and development of brake system for EV and ICE.
Okay, great. Yeah.
Yeah.
Thank you.
Thank you. Thank you.
So you are sitting with the team, Mahindra team.
Yeah, yes, sir. Yes, sir.
Oh, okay. Is there anyone else? Giri Babu? I don't remember calling the name.
Yeah, yes, sir.
Yeah.
Myself, Giri Babu, and I'm working in Nordex India Private Limited. I'm working as an installation design engineer here for 2 years. Before, I was working in Michelin tires as a special purpose machine designer. I completed B mechanical engineering in 2017 at Anand Institute of High Technology.
Okay. So if I know I've definitely missed some people. Dinesh, I see your video now. So
Yes, Professor. So good evening. So I'm Dinesh. I work for Qualcomm Technologies, Bangalore. So I work as a thermal analysis engineer for electronic equipments. So almost I have 11 years of experience, and then I completed my B in mechanical engineering at 2014 from KSR College of Technology, Tamil Nadu. Thank you.
Okay. So let me quickly go through all the names. Anand, I don't remember calling your name. V. Anand.
Good evening, sir.
Yeah.
So myself, Anand, working in Mahindra Brakes.
Sir, working in?
Mahindra Brakes Consulting.
Okay. When did you graduate from
Around
BTech?
15 years back, sir.
So 2010.
Yes.
Yeah. All right. Anyone else? Still remaining to be introduced here. Okay. So if there are no one else, then we will move on to our stuff. So you're able to see my screen, I suppose?
Yes, sir.
Yes, sir.
Yeah. Okay. So I hope all of you have gone through the syllabus for this course, Failure Analysis and Design, before choosing to take this course. Can I assume that you have taken, you have looked at the syllabus? You can just raise your hands electronically.
Electronically.
Yeah. Okay. So if you have, I hope, because that is, you have chosen this course. So I assume that all of you have taken, yeah. So I can see some raising hands. All right, good. I think my screen. There is nothing being written on my screen. Let me redo the screen sharing. Yeah. Okay. So in this course, what we are going to learn is about understanding failure of materials and how we will use the knowledge of failure in order to do the design. And as you would have seen the syllabus, most of it is focusing on failure of metals. The reason for that is most of the engineering components that we deal with as mechanical engineers are primarily metals. However, in the recent decades, a large fraction of plastics have come into our portfolio. So we are also required to deal with polymers as mechanical engineers, whether we like it or not. So as a part of this course, what we are going to do is we will first understand the underlying reasons for failure of different kinds. Whether when a body is subjected to some external loads, when will the body fail, and try to understand the micromechanical reasons for such a failure. And having understood the reasons, and then what are the procedures one needs to adopt in order to carry out the design calculations. This is in a nutshell that we are going to do in this course, right? So before we actually talk about the course, the first thing that I usually do is to spell out what are the expectations of this course and how is the evaluation going to be. So in this course, we will have the following evaluation pattern. So we will have one midterm exam, typically 25% weightage. And then there will be a project. I would call it as a term project. And it's an individual project which will carry 20%. There will be assignments. Maybe midterm project, let us keep it as 15%. Assignments 15%. And final exam, end semester exam, balance. What is it? 30 plus 25, 55. So end semester is 45%. So this is going to be the grading scheme for this course. So the project we will most likely decide. So I will give you a time frame during which you will think about what project you are going to do, and then you will send me the concept of your project or the title of the project and what you are trying to achieve through that project as a part of the course. This is typically, I would expect you to give me this information by midterm exam. By then you would have learned some material. Based on the material that you have learned and what is going to be there after midterm, you can have make an assessment. Based on that, you can propose a project. It could be sometimes it could be implementation of a research article, or you can actually do some experiments if you have experimental facilities in your organization, or you can do some simulations if you're already having some expertise in doing simulations. Okay. So that's the grading scheme. So there are two ways that we will, I hope some of you have already done some courses in your MTech program. So you know the grades S, A, B, C, D, and E. So S is 10, A is 9, B is 8, 7, 6, E is not 5 but 4. Okay. So typically I follow absolute grading. When I say absolute grading, it is pretty simple: 90, 80, 70, 60, 50, 40. Right? No confusion, pretty straightforward. This is absolute grading. But we also do relative grading, if at all the class wishes so. In the relative grading, the class average, let us say average is say X bar. So X bar plus 1 sigma will be B, X bar plus 1.5 sigma will be A, X bar plus 2 sigma will be S, where sigma is your standard deviation, and X bar minus sigma will be D, X bar minus 2 sigma, 2 sigma or 1.5 sigma will be E, and typically X bar will be, your average will be C. Okay. So this is how we take the grading. So this is your chance to decide the grading scheme as well as whether you want absolute grading or relative grading. Once all of us agree, that will be cast in stone. Is that okay? So is the classification of marks or distribution of marks in midterm, project, assignments, and end sem. Is it acceptable to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Everyone is fine with it, right?
Yes, sir.
Okay. So you want relative grading or absolute grading?
Relative, sir.
Relative, sir.
How many of you want relative grading?
Relative, sir.
Huh? Everyone wants relative grading.
Sir, whatever you decide the best.
No, I cannot decide. No, this is democracy. You choose what you want.
Absolute.
Absolute, sir.
Huh?
Absolute.
Can we know
Absolute.
from previous classes what is the mean looks like?
I
Previous
don't know.
experience.
I don't remember, but in the end, it really does not matter. Okay. Because there will be some people who will be doing exceptionally well, some people who may not be doing reasonably well.
Are any relation with the question paper?
Sorry?
Any relation of this choice with the question paper?
No. The question paper will be always tough, irrespective of what you choose.
Then relative is better.
So it does not matter whether you choose relative or absolute. Yeah, it will be definitely tough.
So then
Yeah.
relative is better.
Okay, so let's go with relative. Is that okay? Yeah.
Fine, sir.
Fine, sir.
Yes,
So
Yes,
we are
sir.
going with relative grading and midterm, project, assignments, and SEM. Okay. So let me give you a disclaimer. Let me make a disclaimer. In this course, or for that matter, any course in IIT Madras, there are two things that are extremely difficult. The first thing that is extremely difficult is to get an S grade. Okay. And the second thing that is extremely difficult is to fail in a course. So both of them are not easy, right? You really have to work extremely hard in order to get any one of these two. Yeah, failure is also very difficult. So you cannot fail because I am giving you 15 marks, free marks through assignments, and another 15 marks through project. So 30 marks is already there. So you just need to work for 10 marks, right? If you want to pass, but that's not what you are here for, right? But the marks are aside. Most of you are not in this course for marks and you want to learn something from this. So let's hope that that's how it spans out. Okay. All right. So in this course, there are couple of modules. So this is how we want to deal with this course. What are the modules that you would like to be taught is something that we will decide now. So typically what we start by is with understanding structure of materials. And then we talk about defects in materials. Then we will talk about mechanical properties. Then we'll talk about failure. So in failure, we'll talk about static failure theories, static failure, and then fatigue failure. And then we'll talk about creep failure, then failure through polymers, and if time permits, composites. Okay. We have an exhaustive material to cover, or rather an exhaustive set of information that needs to be uncovered in this course. Okay. So now we need to decide if we spend too much time on these three modules, which you should have learned in your undergrad times. And I know a large fraction of you have been away from academics, and even some of you who have graduated in as early as 2022 might not remember whatever will be there in these first three modules. So do you want me to deal with these three modules? So what basically will be there? The structure of materials. What do you mean by crystal structure? What kind of different crystal structures will be there in the materials? The reason why we need to learn about these things is because that forms the basis for understanding the mechanical behavior of the materials, which will in turn explain to us why materials fail in a certain fashion. So in order to understand the reason for failures, you need to go to the level of understanding the structure of crystalline materials, and then we will be able to make a reasonable assessment as to why a particular material fails in a specific fashion. Okay, that is the reason why we start like that. However, we can cover these three topics rather quickly, or maybe we can you can dwell on it a little bit more. That is up to us to decide. Okay, so that if we finish these three modules quickly, then we will have time actually to spend on these four modules, which probably is pretty new or new to many of you. Okay, so now we need to decide. So now I need the opinion from the class. What is that you want? So option 1 is the first 3 modules are fast paced and then move on to this, or I don't even do that. Option 2 is I don't even do that and actually start with mechanical properties and start to failure. It does not matter, you will be able to follow the material. So which one do you prefer?
Sir, a
Option
quick
one.
run through. Option 1, sir.
Option 1. All of you want option 1?
Yes, sir. Sir, I think it's a unanimous answer.
Okay. Okay. All right. Then I respect your decision. So we'll go slow, right? That's what you're saying. We will definitely do that. Okay. So in that case, I will start with my slides and then we will move on slowly. Is that okay? 1 minute. Let me
Okay,
open.
sir.
Sir.
Yeah. Yes, is there a question?
Yes, sir.
Yeah, please go ahead.
So no question, sir. We can proceed.
Oh, okay, okay. So are you able to see my screen? Yeah. So we'll start with the structure of materials. Particularly what we are talking about is structure of crystalline materials. Okay. We are not talking about amorphous materials. We are only going to talk about crystalline materials because that is what we are mostly dealing with as mechanical engineers. Okay. So we need to understand what is a crystalline solid and what is a solid to begin with. So solids are materials which have some regularity of the atomic arrangement, or crystalline material is one such is one in which the atoms are arranged in a repeating or periodic order over a long range order. Okay. So what do we mean by this long range order? So in a crystalline solid, most important thing is that the atoms should be arranged in an orderly manner. That is the most important requirement. But it is not enough. It is a necessary condition that there should be order in a crystalline solid. But that's not enough. What is more important is that the order should be long range. So you should have a long range order. That is the most important requirement for a crystalline solid. So what do we mean by long range order? So let us do this thought experiment, right? So if you are sitting, imagine yourself sitting in a classroom. Okay. So let me draw this picture from the top view of a classroom. So there are students sitting like that. Those circles are heads of the students. Okay. And if you look at this fellow, you can see that to this person's right, left, top, bottom, at equal distance, the person finds another neighbor. Okay. Now, if you look at this fellow, again the same thing. If you look at this fellow, he also finds 4 neighbors. So imagine yourself, you are going and sitting there and observing the surrounding environment, whether you, let us say this is position A, position B, position C. Irrespective of where you are sitting, whether you are at position A, position B, position C, you are observing the environment to be the same, isn't it? So now that means the point A is experiencing same environment as point B and point C and so on. Suppose if this guy A, so let us say this arrangement is extending to infinity. That means you are sitting in a class that is sufficiently large. So no matter where you are standing, at whichever student position you are standing, you will observe exactly the same environment surrounding you. And if it happens over a long range, what do I mean by that? Over, for example, if you talk in terms of human scale, if you find the same environment at when you are sitting in Chennai, and if you are observing same kind of environment everywhere, say up to Bangalore, that means such an order is what we call long range order. So, but Chennai and Bangalore are in our human terms, but you need to explain this in terms of materials. So for materials, what we actually mean is that several atomic distances. So suppose if we, let us say this is an atom and the surrounding atom is sitting at a position at a distance of x, let us say, or A, and several thousands or millions of atom distances, the order exists. That means the environment will remain the same over several thousands of million of atom distances. If such an order exists in a material, such a material is called crystalline material. Okay. So why it is important? To understand how these materials are arranged. So now if you look at this fellow, sorry. So in this guy is surrounded by, let us say, an atom on a circular path. So this person is seeing atoms around him or her at equidistance. So at any direction he is seeing around 6 neighbors around him or her, right? If such any position, if the person goes and surrounding him, or there are 6 neighbors, imagine, and this 6 neighbors the person should be seeing anywhere they move, such an order is called long range order. And the material properties that we are going to discuss in future classes will essentially depend on such a long range order. And most all metals and some ceramics and some class of polymers are capable of forming crystalline structures under normal conditions. And that is the reason why it is extremely important that we study these systems. Okay, so why should we care about crystal structure? Because important physical properties such as electrical conductivity, thermal conductivity, right? Magnetic permeability, magnetic properties, elastic stiffness and strength of these materials, all these things depend on the kind of crystal structure. That is the reason why we need to understand the structure of the material. So in order to understand crystalline structure, we need to first understand the language in which these crystal structures are to be identified or to be described. So typically the crystal structures or crystalline materials are characterized by repeating structures in 3D. in 3 dimensions, the same structure should repeat. So before we understand this, the meaning of repetition in 3D, we should understand these 3 terms called lattice, lattice points, and unit cells. These are the 3 terms that we should understand to be able to make sense of a crystalline structure. Okay. So now, first of all, let us focus on finding what is a lattice. How to identify a lattice? If you have a repeated structure in 3D, and what do you mean by lattice of that structure? Okay. So identifying lattice is pretty simple. All that you need to do is choose an arbitrary reference point, any reference point, and mark the points that are identical to the reference points in the pattern. And this set of identical points are called lattice. Okay. When I say that in words, it's not very clear, but let me show it through this. Let us observe this brick wall. Okay. In this brick wall, what is the guideline to identify a lattice? Choose an arbitrary reference point. Any reference geometry you identify in this lattice. Okay. And then start identifying the identical points. So let us say I have identified that reference point. Earlier it was like that. Now I have identified that reference point. So that brick is my reference brick. How is that brick? So this is a small brick with a larger brick above, 2 larger bricks besides, and 2 larger bricks beneath, and which is actually centered to the 2 larger bricks. So I am talking about these 2 larger bricks besides, and this brick, and which are not centered, but this guy is centered around these 2 bricks. Correct? Now, let us try to identify a similar points. If I look at this fellow, this is a similar point. Do you agree?
Yes,
This is a similar point.
Yes.
That is a similar point. Is this a similar point?
No.
That is not, right?
Yes.
That is not a similar point, isn't it? So I cannot take that. So now next I am trying to identify a similar point. So this is a similar point or not?
Yes, so that is similar.
Yes.
So let us try to identify all such points. Right? Are there any such points? Any more points like that in this lattice that we did not identify? It does not matter because this structure is repeating in 2D. This is what we call a 2-dimensional lattice. In order to drive the point, it is easier to describe how to identify a lattice in 2D. The same concept goes in 3D also. But we have identified almost all the points. And then for the structure, this is the structure that we are looking at. For the structure, we are trying to identify a lattice, right? So we have identified one reference point and identified all the similar, equivalent, or exactly same kind of reference points in the structure. Now you remove the structure and these are our points, right? And this is what we call lattice. So in this fashion, if you keep repeating, then you will form the lattice in 2D. So this is the lattice that describes the structure that we have just now erased. But is this the unique lattice for this particular structure? Need not be, right? Because instead of choosing this fellow, I could have chosen, say, this fellow. If I have chosen that fellow, can we identify the lattice points? If I have chosen that fellow, then I have to look at the brick which is, this is identical or not?
Yes, sir.
Yeah?
Yes, sir.
And similarly, this is identical?
Yes, sir.
Similarly, this is identical, right? Similarly, Is this identical?
No, sir.
That is not. Very good. So you could have identified a different reference point and would have got a different lattice. But all of these lattices, different lattices for the same structure. So that means depending upon the choice of the person who is constructing the lattice out of a structure, the lattices could be various, meaning could be different from each other, but all these lattices correspond to the same underlying structure. So the idea of lattice is just a geometric point of identical nature, which would construct, which is when expanded in 2D or 3D, will give you the picture of the actual underlying structure. Okay, is that clear? So now let us look at the second definition.
Yes, sir.
Yeah. Next is unit cell. What do you mean by unit cell? So when we talked about lattice, we talked about a point. Now we'll talk about unit cell. These are basically repeated elements in 3 dimensions. But when we are describing it, we'll show it in 2D. But whenever we are discussing crystal structure, it should be a 3-dimensional repeated structure. That is why it is a repeated element in 3 dimensions. So unit cells that we have learned in our high school, they are the building blocks of our crystal structure. And now you can have 2 kinds of unit cells. One of them are called primitive unit cells and another one is non-primitive unit cell. So let us look at this point cloud. This point cloud is what you call lattice points. And from these lattice points, I could construct this unit cell, right? And now if I take this unit cell, because I am talking about 2D, how do I construct my lattice? I should translate this fellow in both x and y directions, right? So I could construct, this is my and y direction. So in order to generate this structure, this crystal, I have this is a lattice point, and when connected with these lattice points is my unit cell. Okay. So I'm erasing that. But to describe a crystal, do you have to have only one unit cell or can I have multiple unit cells like what I have seen in the previous brick example? One can have multiple unit cells describing the same crystal structure or same lattice structure. So here this is one unit cell and this one is your second type of unit cell. This will also, when it is expanded, when it is translated, will fill the space, right? Whenever you are taking a unit cell, whenever it is generating a crystal structure, this unit cell, when it is translated in both the directions, both the coordinate directions, it should not leave behind any spaces. That is the first requirement. Then only it is a valid unit cell. If it is leaving behind any spaces, then it is not a valid unit cell, first thing. And the second thing is, you should be able to fill the space only by translation in both the coordinate directions. You cannot rotate the unit cell. And only then that is a valid unit cell. You should be able to fill in the space by only translation, but no rotation. Okay, so these are the 2 requirements. So now we have seen 2 kinds of unit cells. One is a unit cell in which, if you look at this particular guy, now let us carefully look at this fellow, this unit cell, and I will draw the neighboring unit cells also for this fellow. And let us look at this atom. or this lattice point. This lattice point or unit cell corner is shared by how many unit cells? 1, 2, 3, 4. So this guy does not only belong to 1, but it also belongs to 2, 3, and 4, which means this lattice point is equally shared by all the 4 unit cells. That means this is only 1/4 of this point belongs to each of the unit cells. So for effectively, for one unit cell, how many atoms are there? There are 4 atoms, each having 1/4 participation. So in this particular unit cell, effectively you have 1 atom or 1 lattice point. Is that clear? Is that point clear, whatever I have made just now?
Yes, sir.
So if a unit cell has only 1 lattice point, then such a unit cell is called primitive unit cell. Now let us look at the other unit cell, this fellow. Let me construct the neighboring unit cells for this fellow. 2, okay. Now, in this unit cell, for example, if I take this fellow, I have 1/4 of this, 1/4 of this, 1/4 of this, 1/4 of this, isn't it? So you have 4 into 1/4. But in addition to that, you have a central lattice point. So that lattice point does not belong to any other unit cell, isn't it? It is exclusively, completely for that particular unit cell. Similarly, this lattice point is completely for this unit cell. So in addition to 4 times 1/4, but you have plus 1. That means you have 2 lattice points per unit cell. So you could choose, both of them are valid unit cells, wherein one of them has effectively 1 lattice point per unit cell, the other one has 2 lattice points per unit cell. If a unit cell has only 1 lattice point, then such a unit cell is called primitive unit cell. If a unit cell has more than 1 lattice point per unit cell, and such a unit cell is called non-primitive unit cell. It is just a definition. But sometimes if you come across what is a primitive unit cell and non-primitive unit cell, effectively a primitive unit cell will have 1 lattice point, a non-primitive unit cell will have more than 1 lattice point. That's all it means. Okay. So now if you look at this particular lattice, when I say lattice, I am only talking about these points. Okay. If I did not draw these figures to begin with, you could find out how many such unit cells are possible. This is 1 unit cell that is possible. This is 1 unit cell that is possible. This is another unit cell that is possible. What is the meaning of saying that this is a unit cell that is possible? Meaning, if I take this unit cell, if I take this unit cell, I call these two guys as lattice vectors. This is lattice vector 1, let us say E1 and E2. Now, I take this unit cell along the edges, unit cell edges will form my lattice vectors, okay, E1 hat, E2 hat. And now, I translate this unit cell by how much amount? By this much amount. Whatever is the lattice width in that particular coordinate direction, lattice size, and I translate in this direction or in this direction. I should be able to do that translation. And am I making any open spaces? Am I leaving behind any voids? I am not. And this is E1 direction. Similarly, I could do that in E2 direction infinitely. I am able to fill the entire space, isn't it? Since I am able to fill the entire space, then this is a valid unit cell. Now, if I take this fellow, If I take this fellow. Now this is one unit cell edge and this is another unit cell edge. So for this particular unit cell, this is my E1 hat and E2 hat is not vertical like this. This is my E2 hat. So the lattice vectors in this case are this. These are the lattice vectors for this. For this fellow, E1 hat remained the same, but E2 hat is different. Now I should, if this is a valid unit cell, I should be able to translate it in E1 hat direction and E2 hat direction and fill the entire space. And you will see that it will be possible to do so. And hence this is also a valid unit cell. Similarly, this is also a valid unit cell. But if you carefully observe, among these, which one are the primitive unit cells and which one is not a primitive unit cell? So let us call this as 1,
So blue,
2,
okay.
and 3.
Sir, 1 and 2 are primitive, whereas 3 is non-primitive.
3 is non-primitive because this guy is shared by 2 of them. This guy is shared by 2 of them, and these 4 corners are shared by 4 neighboring unit cells. So effectively, how many lattice points are there in this unit cell? 4 into 1 by 4 plus 2 into 1 by 2. Isn't it? That is 1 plus 1. There are two lattice points are there. Is that clear to all of you?
Yes, sir.
Yes, sir.
Yeah,
Yes,
sir.
Professor.
Okay, good. So by definition, all parallelograms, you can construct any parallelogram in a system, and that will be a valid unit cell. And of course, square is the smallest with most symmetry. That means, what do you mean by symmetry? We will talk about it in a moment. Okay. So now let us look at this structure. In this structure, let us try to identify unit cells. Like in the previous case, you have 3 possible unit cells, right? Similarly, in this structure, if you look at, this is one unit cell. And this is another unit cell. Where do you get that? Let me draw it with a different color. The second that is your second unit cell, as you can see here. Right? Where is your third unit cell? That is your third unit cell. You can see here. All these are valid unit cells. You just tile them and you will be able to fill the entire space without leaving any gaps behind. Okay. So I have talked about lattice, and many times we get confused between what is a lattice and what is a crystal. What is the difference between a crystal and a lattice? Okay. So this is important that we fix that confusion. So a lattice is simply a translationally periodic arrangement of points. If you're only talking about points, that is what a lattice is in 3D. All these points, if they are occupied by atoms, then it is called a crystal. That is the only difference. So lattice is only a geometric concept. And if these points that you are identifying, if they are occupied by atoms, then it is called a crystalline solid occupied by atoms of iron, atoms of gold, atoms of silver, a crystalline gold, crystalline silver, crystalline iron, crystalline copper. What is the meaning of that? The lattice points are occupied by that particular element or particular atom. Okay. So if I have to, let me see if I have the animation with me. If that is there, then it will be much easier to drive the point. Okay, I don't seem to have. Maybe I will borrow that particular slide just to show. Yeah. You're able to see the screen now? Yeah?
Yes, Professor.
Yeah. So this animation would be useful. So that's why I'm switched to this fellow. So this is what earlier I was talking about. If I show you only this set of points, you could identify that as one unit cell, that is another, and that's another, right? So this could be another set of unit cells. You can identify that is one unit cell. Can you identify, say previously in this particular arrangement, when you have seen this arrangement, you are able to make square as a unit cell, isn't it? Now let us look at this arrangement. Will you be able to make square as a unit cell, as a primitive unit cell?
No, sir.
You cannot. So the unit cell will be, the smallest unit cell only can be a parallelogram. It will be a primitive unit cell, but the symmetry level will not be as much as a square. And here you can have another unit cell and so on. So what the point that here we are trying to say is that a square has higher level of symmetry than this. We will talk about that. So sometimes you may not be able to choose a unit cell which is having the highest level of symmetry. And let's not dwell too much on that. We will move on and then try to understand the concept of lattice and unit cell. So lattice and a crystal. Okay. So now, as we said, lattice is collection of points. If those points are occupied by atoms, then it is called crystal. So in other words, crystal is lattice plus some motif or basis, whatever is sitting at those lattice positions. So basically what lattice tells you is how to repeat the structure, and basis is what to repeat at those points. So you typically have 6 lattice parameters, and you have a lattice cell from which you can generate lattice, and without motif, only when you put motif at those lattice positions it becomes crystal, otherwise it is not a crystal. That point becomes more clear with this example. So let us say you have lattice, there are points in space, these are lattice, and now if you add a motif, heart as a motif, then meaning what? At these points you have to put a heart. Then you have a love crystal. Similarly, if you replace this heart with copper, then you would get copper crystal in which the copper atoms are arranged in this fashion. If you get a gold, add as a gold as a motif, then you get a gold crystal where the gold atoms are arranged in this fashion. Is that clear now, the concept of lattice and a crystal? So lattice is only a geometric construct where you are telling how the points are arranged, and at those points what needs to be kept is decided by this motif or basis, and depending upon what the motif is or what the basis is, that particular lattice becomes a crystal of that motif. Okay. Any questions here? Is this concept clear?
Very clear, sir. Thank you.
Good. All right. So whenever you're talking about a unit cell, in 2D, until now, I have only talked to you, I have only shown you 2-dimensional examples because that's easier to drive the point. So in 2D, any parallelogram whose vertices are lattice points will be a valid unit cell. Similarly, in 3D, any parallelopipe whose vertices are lattice points. And as we have discussed, you can choose infinite number of unit cells. And typically, it does not matter whatever is the chosen unit cell. If you repeat that, you will form a crystal or you will form a lattice. And typically, for understanding the structure of atoms, the general practice is to choose the smallest unit cell as a reference, but it is not necessary that you should choose only smallest unit cell. Okay. All right. So now I would like to see why only a parallelogram will be a valid unit cell, right? So let us go back. In this particular scenario, let us see what happens when it is not a parallelogram. Let us choose a triangle. Okay. Let's go back. So let me choose a triangle as my unit cell. If I choose a triangle as my unit cell, first of all, let me translate along this direction. Are you able to see my mouse or no? I don't think so. Let me translate this triangle in this direction. Okay. So if I translate my triangle in that direction, the next triangle will be this fellow. Do you agree? Now, if I continue to do that, like that, and most importantly, the edges, the vertices should be occupied by the lattice points. Now, if I take this fellow, now you have this space, right? How will I fill this space? If I am only doing the translation of these triangles, is there a way that I can fill this space? Or for that matter, this space? Because I have only created, that is the triangle, next is the triangle, next is the triangle, this triangle.
No, sir.
The only way that I can fill this space is by rotating this triangle. I can put it inverted, right? Then I will be able to fill in, isn't it? But without rotating, only by translation, I will not be able to fill the entire space. And that is precisely the reason why your triangle cannot be a valid unit cell. Okay. So that is the only parallelograms allow us to do this translation without leaving behind any voids in 2D. Similarly, in 3D, it is not a three-dimensional geometry. That is a parallelopipe. Equivalent to parallelogram in 3D is a parallelopipe. So that will allow us to fill the space without having any voids left behind. Okay, all right. So now we talked about another 5 minutes. Let us talk about, quickly introduce the concept of symmetry of crystal structure. So we have two types of symmetry. One is rotational symmetry. Another one is a translational symmetry. So a material which possesses both rotational as well as translational symmetry is what is called a crystal. If a material does, if a geometry does not have both translational and rotational symmetry, it cannot be a crystal structure. It cannot be a crystal. Okay. So if a material that does not possess both the symmetry, means it neither has translational symmetry nor has rotational symmetry. That means there is no order at all to this material. Such a material is what we call amorphous material. We only learnt about crystalline materials and amorphous materials in our colleges, but the crystalline material will have order everywhere, both translational order as well as rotational order, whereas an amorphous material will not have, neither has a translational symmetry nor rotational symmetry. But if a material has a rotational symmetry but no translational symmetry, that means it is half satisfying the symmetry requirement, then such a material is called quasi-crystal. We will not discuss about them, but we know we are only going to talk about crystalline materials in this class and their failure phenomena. We are not even talking about the failure mechanism of amorphous material. For example, can you give me an example of an amorphous material? Rock, glass, yeah. Okay, so now let us try to understand the rotational symmetry. Cube, or in now I will show you a square which has a four-fold rotational symmetry. What do I mean by that? So let us look at this particular square. Okay, pay attention to these points, corner points. If I am rotating this square about its centroid, about its center, I have rotated it by 90 degrees. In order to show that I have rotated, I am showing it here. Okay, but let me say this is rotated by 90 degrees. When it is rotated by 90 degrees, these lattice points, although I am showing them on 4 different colors, the reason why I am showing them in 4 different colors to show that it has rotated, but the geometry has gone back to the same lattice points. Can you see that? Can you see what I mean here? So this lattice, if you rotate this fellow, only when you rotate it by 90 degrees, again, all the lattice points will be occupied by the corners of the square. If you rotate it by less than 90 degrees, the lattice points are not occupied by the corners of the square. Can you imagine that?
Yes, sir.
Yeah. Again, another 90 degrees, again another 90 degrees, again another 90 degrees, it will go back. That means this cube will have, that means you will not be able to distinguish on which side you are sitting, because in all these rotational configurations, the lattice points are identical in nature, because each lattice point is occupied by the same kind of an atom. So whether you are on this line or on this line, you will not be able to distinguish, because this all environment is same. So in order to get there, you have to rotate this square by 90 degrees. So if you look at the total rotation angle 360 degrees by theta, if you put 90 degrees, then you get 4. Then that is what we call four-fold symmetry. For example, if you rotate it by 45 degrees, then we generate new points which are not the lattice points. Then it is not a symmetry. For 90 degrees, we don't generate new points, and hence it is called four-fold symmetry. Similarly, a cube. So if you take now I have shown you a square. Imagine this cube. This cube can be rotated about x-axis by 90 degrees, and you will again will not generate new lattice points. You will be occupying the same lattice points by rotating by 90 degrees about x-axis. All of you agree with that?
Yes, sir.
Yes.
Yeah. Similarly, you can do so by rotating about y-axis or not?
Yes, sir. That also.
Yes, sir.
Similarly, you can do so by rotating about z-axis. So that means a cube has 3 four-fold symmetries. 3 means one about x-axis, one about y-axis, one about z-axis. The cube has highest level of symmetry, 3 four-fold symmetries. But this cube also has, instead of 90 degrees, if you rotate it by 180 degrees, then also it will show symmetry or not?
It will show symmetry. So
Then it has two-fold symmetry, because by rotating by 180 degrees, 360 by 180, it will have two-fold symmetry. Is two-fold symmetry as a higher level of symmetry than four-fold symmetry, or otherwise?
Higher level.
Four-fold symmetry is higher level because there is more levels of symmetry, and hence for any geometry, the symmetry is described by its highest level of symmetry. Although the cube can also show two-fold symmetry, because it can show four-fold symmetry, this cube is considered as a four-fold symmetry geometry. Okay, although it can show two-fold symmetry as well. Similarly, rotational symmetry, that means if you imagine there is a unit cell here, there is another unit cell here, there is another unit cell here. If you move the unit cell, if you translate it by the same amount, you will not meet new lattice points, meaning you will not generate new lattice points. Already existing lattice points it will occupy if I translate it, isn't it? And in the y direction also. That is why a cube also has a translational symmetry. Okay, so let us leave with that thought. In tomorrow's class, we will discuss a little bit more detail. I know it may not be clear to all of you at this point of time, but let us leave with that thought, and then in tomorrow's class, we will discuss more on the symmetries. I request all of you to type in the chat box that you are present. That will mark your attendance. If you have any questions, I'll be happy to take. Otherwise, we will meet tomorrow.
Thank you, sir.
Okay.
Thank you, sir.
There are no
That
further
was very
questions, so
clear.
let's see each other tomorrow. Yeah.
thank you, sir.
Bye.